All right, so we'll take our usual look at the calendar. Today we continue talking about the sequences, but we'll specifically be talking about populations and linear growth, whatever that means. Next class we will continue with populations, but we'll talk about something called exponential growth, and then one more class before the test. The apportionment project is due Monday, coming up, the very next class. So you have 5 days between now and then, but you're not going to see me in class between now and then. So if you have questions, you got to get going on this project so you have a chance to ask them and get them answered, okay? Any questions on the calendar? Okay. So here we are. We'll start at the top. In fact, I want to jump around a little bit here. I want to start at number 5, and then we'll go back up and fill in some of the vocabulary stuff here. So let's go to Nicole for number 5.
This reactor has 100 tons tanks already reacted. Let's create recursive and explicit formulas P and how long it takes.
Okay, so P sub n is going to be the, quote, population of the tank, how much nuclear waste or radioactive waste is in the tank in year n. So if we start off by saying that P0 is the initial amount, how much stuff is in the tank initially? It's 35 tons. So we're going to start with P0 as 35. That 0 indicates it's the start of the experiment. P1 is going to represent the amount of stuff in there 1 year after we started. That's the 1. It's 1 year later. And we're generating 5 tons a year. So how much stuff is in there? 40. P2, which is 2 years after we start the experiment. Again, it's 5 tons per year. It's 45. And you can continue like that. All right? So let's first think about this recursive business. Pn equals Pn minus 1. I'm going to write that. For almost every single recursive formula I ask you to come up with, it's going to start like that. Now this equation is not correct. We need to stick something on here at the end. But the equation so far says if you want to know what's going on currently, you take a look at 1 year ago and then you do something, right? In this case, what do we do to 1 year ago's number? We add 5? Yes? So we just put plus 5. So that right there is the recursive formula. The important thing again is to recognize that P sub n is the current term, and in order to figure out what's happening right now, we look 1 year ago. That's the Pn minus 1. In this case, it's add 5 every year. Could be a different rule for other problems, but that thing in red is very common in terms of starting to write down the recursive rule. Okay, the explicit formula is oftentimes harder to come up with, but far more useful. We'll start the same Pn equals, but this time the recursive rule, this time you're not allowed to look at some previous information. You're just trying to zip directly to the answer. So would you guys buy something like this, 35 plus something? We start with 35, and then what's our way to, all right, so plus 5 I like, but there's one more piece missing, is n. That's our way of mathematically saying add 5 every year. Is that plus 5n. So for example, if you wanted to look at P3 using this black explicit formula, we'd say, oh, that's 35 plus 5 times 3, whatever the n is that we wrote down there. So that's 35 plus 15. 50, is that the next number in the list? 50? Yeah, so it works, okay? All right, so that's good. And then the other part that Nicole read to us is how long will it take for the tank to fill up? So there's one other piece of information in this problem we haven't used yet. What is that? Is the 100, Griffin? Griffin has the answer already. Is it 13 years? Is that what you said? Okay, so let's see if we can get to Griffin's answer. So we know that the capacity of the tank is 100. Is 100 the value of n, or is 100 the value of P sub n? It's P sub n. You want the amount of stuff in the tank to be 100. So we just change this equation so that it says 100 equals, and then we copy everything else. And this is one of the few moments in this class where we are asked to do some algebra. So solve that for n. What do we need to move first, the 35 or the 5? The 35. We do that by dividing both sides by 35. Subtract 35 from both sides. Okay, so we can do that. So then we go 65 equals 5n. And then what number needs to move? 5. Subtract 5 from both sides. Divide by 5 from, I'm just not having a good day so far. So we take 65 and divide it by 5. And lo and behold, 13. Right? 13 what? 13 years. N is just the time unit in this problem, it's years. So in 13 years, this tank will be at full capacity, and we need to do something about that. Questions on that? Okay, so let's go back up and just talk about some of this stuff that that I skipped over initially. So a population growth model is just a way to describe how a population is growing. In the example we just looked at, the population wasn't people, it was amount of radioactive waste, but it was just something that was growing, you know, year in and year out. Population could be humans, could be rabbits, could be money in a bank account, anything that grows. And we're going to talk about population as a sequence of numbers. So we saw P0 was the size of the initial population, how much stuff was initially in the tank. And then P1 was how much stuff was in the tank after 1 unit of time, 1 year had passed, right? And then P2 and then Pn is going to be our generic kind of thing. The only difference from the notation we've got here compared to what we did on last class is that last class our first number was P sub 1. We didn't start with P sub 0, we started with P sub 1. So I just want to highlight that today our first number in the list is always going to be P0. That 0 again represents an initial thing. We're starting the clock at time 0, right? If you start a stopwatch, it says 0. It doesn't say 1 and then begin to count. Okay, 3 says we're interested in the transition rules. Those are the rules that tell you what happens to the population at each transition. What happened to the population every year in this? It went up by 5. That was the transition rule, up by 5 every year. Okay, and the this radioactive waste example is something called a linear growth model. Inside of that word linear, we see the word line. And where we had this equation that was black, this 35 plus 5n, if I change that to 35 plus 5x, and I call it y equals, then maybe it's starting to look familiar based on some old algebra class of yours. Anybody know what the graph of that equation is called? It's a line. It's a linear equation. If you graph that thing, you will see a line. It's going to hit the y-axis. You guys remember the y-intercept? So this is kind of taking us a little bit afield from where I want to be, but maybe you've got memorized in your brain somewhere y equals mx plus b. B is the y-intercept. What is it in this problem? It's the 35. So this guy starts at 35. And then what's the 5 called? That is going up by 5. What was it called in algebra class? It's called the slope. And it says every time you run 1 unit to the right, you go 5 units up. 1 year to the right, 5 units up. 1 year to the right, 5 units up. If you graph that line, you'll get something that represents what's happening in this container. Okay, we don't need to worry about the whole slope stuff, but I did want to kind of ground this in things that you've seen before. Okay, so we needed 2 pieces of info. We needed the starting amount, which was 35, and then we needed how much the population grows by per transition. So a linear growth model is one where we keep adding the same amount over and over again. In this problem, it was 5. Next class, we're going to talk not about adding the same amount every time, but multiplying by the same amount. Maybe multiply by 2 every time. In fact, there's a sequence. If you look on the colorful sheets of paper around the walls here, one of these is multiply by the same thing every time. You see it? What color? Looking just at the bottom row, not the top row. What color says multiply by the same number every time to get the next number? Is it? Blue. If you look at the bottom row of blue, what do you have to multiply the 2 by to get the 4? Multiply by 2. 4 to 8. Multiply by 2. 8 to 16 times 2. And you can see how quickly these things get. All we did is multiply by 2 20 times, and we're already over 1 million. Grows really quickly. So this is not add the same amount every time. This is multiply by the same amount every time. We'll see those next class. Today, it's always going to be add or subtract the same amount every time. Okay, and then this last piece on this page, it says the 5 in the above problem is called the common difference, since 5 is the difference between populations in any 2 successive years. So for example, 40 to 45, what's the difference? 5, of course, because we added 5 to get from one number to the next. But we call it the common difference because when you subtract 2 terms, that's what you get. So for example, let's jump down to 777. Says here's some formulas that you don't need to memorize, but Pn equals, what was the start amount for the radioactive waste? It was 35. Then it says plus n times, what was the common difference? It's 5. Is this the formula we came up with? 35 plus 5 times n. That's it, right? So the formula is written here, but it always works. It always has this particular form. You don't need to memorize it. I'll give it to you on the test, but it's there if you want it. Or you can think about the recursive formula, which is over here. It says Pn equals Pn minus 1. That was the, we just start that way almost every time. Plus, what was the common difference? 5. Was that the recursive rule that we wrote down? Yeah. So there are formulas that you can use. Personally, I like to really try to think about the setup of the problem and try to figure it out. But if you like formulas, there they are. Those are the 2 formulas for linear growth models. We'll see 2 more formulas next class that have to do with multiplying by the same number every time. Let's take a look at number 6. Alicia.
In some cases, we are given different starting information. You find recursive and explicit formulas for and in a linear model if you know that 3 equals 28.
Okay, let's spend a few minutes, maybe like 5 minutes in your groups on this one. This is not easy. Should take a little bit of time. See if you can answer this in your groups. Okay, so without really knowing much about formulas, I think some people intuited that we needed to figure out, okay, we went up by a total of 12 in this problem, but how many steps did it take for us to get up there? It was 3 steps, right? Going from P3 to P6. You got to go up P4, P5, P6. So you gain 12, and you gain 12 in 3 steps. This 3 was the 6 minus the 3. So that means that we divide these 2 guys and we get 4. And what is 4 called in this problem? It's the common difference. It's like the 5. Okay, so if we're going to write a recursive formula, I always start my recursive formulas by writing that. Pn equals Pn minus 1, and then blah, there's something coming, but that's how it starts. And then what do we put at the end here? Plus 4, because we gain 4 every time. Go to the previous number, add 4. That's what that says. Okay, then the explicit one is a little bit tougher though, because the explicit one, let's see, well, we have some of the information. It's supposed to be n times the common difference. So n times, again, the common difference was 4. Then there's a plus in the front here, but the starting amount, we don't know it yet. So we got to find it. Is the starting amount P1?
No.
It's P0. 0 is always our start. Again, imagine a stopwatch. It begins with straight zeros. So how do we find P0? Well, if you add 4 every time you step forward, then you better be subtracting 4, stepping backwards. So 28 goes backwards to 24, to 20, and then to 16. If you're feeling very fancy, then you could just say, oh, I'm taking 3 steps and they're each worth 4, so just subtract 12. That's if you're fancy. So what do we get here? P0 is 16, so the formula is always the start amount, 16 in this case, plus n times the difference. Questions on that? Okay, let's move on to 8. Damien.
During the next 2 years, the manufacturer
Everybody know what a widget is? No, it doesn't matter. Anybody know what it is? I think it's just a gadget. I think it's just a generic name for some. Yeah, I think it's just some. Well, look it up. I just think it's something. It's just like a generic name for something we could produce. Okay, so we start with 387, and we're going to increase our inventory by 37 of these guys per week. We know it's going to be a hot seller, so we're going to make a lot of them and store them. So the question is, how many widgets will the manufacturer have on hand after 20 weeks? So without any formulas that we've used today, do you guys have an intuition about how to answer this problem? Casey? Yes? How's that sound? Right, we're getting 20 weeks worth. Okay. So I'm going to write something, and then we're going to ground Casey's intuition in the formulas that we've got up above. So Casey says we're going to take the 37 widgets per week and multiply by 20 weeks. What is that going to represent? How many they made. But then Casey says you have to add 387 to that because that's what we start with. Okay, that seems reasonable. What's the number?
I got 1127.
No problem. Okay, does that seem reasonable?
Yeah.
Okay, so we don't need the fancy formulas, but I just want to show you we could think about the fancy formulas. I'll use the explicit version here. P sub n equals start amount, 387, plus n is just n, times what's the common difference? 37. Every week you gain 37 of these things. Right, so that's just using the formula from up above. And how does the 20 weeks play into this? Just substitute 20 is the n, right? N is how many time units have passed. So then if we wanted to use this, let's say, oh, I'm really interested in P20, which just means change the n into a 20. 387 plus 20 times 37, which I can do in my head because I'm just that smart. But it's just Casey's calculation, right? So I'm just showing you intuition agrees with the formulas. I'm just giving you more practice with these formulas. Okay, part B, we've actually already answered. How many widgets will the manufacturer have on hand after n weeks? That's the formula we wrote in black. That's it, right? That's how many we'll have after n weeks. It's only one of them. Is that black formula explicit or recursive? That's explicit. So we still need to write the recursive one. So my recursive formulas almost always start exactly like this. Pn equals Pn minus 1 and then something. To get the current one, look at last year's, last week's, whatever. And then we plus 37. Just take whatever you had last week and add 37. And that is this right here, plus the common difference. It always works that way for linear stuff. Okay, so just to be clear, the explicit one is this guy up here, and then the recursive one is this one here. See if you guys can answer part C with your neighbors. It says, how many weeks until the manufacturer has 720 widgets? I know a lot of people had the right intuition for this problem, but I want to make it clear that you can just use that explicit formula to do anything you want to. If we're using this guy right here, 720, is it the PN or is it the N? It's 720. It's the PN, it's the population. It's not 720 weeks, it's the population, right? So the equation we just copy, 720 equals, and then you get to do algebra, which you're familiar with, and you solve. And what is the answer here? 9. 9 weeks. Okay, so there's two different kinds of things that I can ask you to plug in. I can give you the population, like 720 widgets, or I can give you the time, like 20 weeks. It's just, you just got to know which one goes where and then find the other one. Okay, next page. Let's see, so we talked about number 9 already. Let's go to number 10. Barb.
Let's say the widget means
Why is this a hard question?
$10 per widget.
It's $10 per week per widget. Yeah. Why is this a hard question? Yeah, we're manufacturing, so the number of widgets you have every week changes, right? Okay, so that's what makes this hard. So we're gonna start off by doing this maybe in the only way we know, and then we're gonna recognize that we need a shortcut. So for example, let's come over here and we'll just make a table, n and p sub n. What's the smallest number I should put for n?
0.
It's 0, right? 0. Yeah, and initially we had 387. And let's go ahead and fill in the numbers for 1 and 2. Okay, so we had 37 the first time, and what do we get? And let's add one more column here. What's the other kind of relevant thing? So the time we have in the ends.
$10.
Yeah, we need to use the $10. So how about we come up with a cost right here? So how much does it cost us for, well, say cost per week? So for that first week there, we have 387 widgets. It costs us $10 per week per widget. So you guys buy 3,870, just multiply by 10. The next week we have more widgets. It's going to cost us more money to store them. How much will it cost the next week? 42.40, and then one more 610. I hope we turn a nice profit on these because this is very costly. Okay. ... I want to write down the last number in this list. I don't want to write them all, but just the last one. We're doing this for how long? So it's 104 weeks, is that right? 2 years altogether? Let me ask this question. This 3,870 is the cost of 1 week, right? That's like your first full week cost. This right here is the cost of the second week, yes? This right here is the cost of the third week. Notice that the third doesn't match that number. You see that? This is the cost of the third week, but it's only numbered 2 over here because we started at 0 instead of starting at 1. So you guys are saying, yes, 52 weeks times 2 years is 104, but 104 is not the last number that goes in this list. It's really 103. 103. I'll just write down here, this is the first week, this is the second week, this is the third week, and point out that those numbers in purple are 1 more than the numbers in black. So when I want to come down here, yes, I want to pay for 104 weeks, but the number that must have come from was 103. Do we see that pattern? We're going to see this pretty often. In fact, I think in every other example we do today, we're going to see that when you go for a certain amount of time, you always end up off by 1 at the end because we started at what number? Because we started at 0. So instead of going from 1 to 104, we go 0 to 103. How many numbers are in that first column, including all the ones that I didn't write? How many numbers are in there? There's 104. I mean, we've got 104 weeks that we're paying for. There are 104 numbers in this list. It just happens it doesn't go 1 to 104. It goes 0 to 103. It's just shifting them up by 1. So very common. Starting at 0, you're going to have to take your final number and make it 1 less than you think it should be. Okay, let's go ahead and fill in the blanks here. I want the population when n is 103. You guys have a formula? So let's use the explicit formula right there. So the formula was so what do we get when we crunch through? Again? Anybody else get that? Is that okay? And then how much will that cost us? 41,980. Oof. And that 41,980, that's how much we pay just for that 1 week. That's not the total. That's just 1 week. Okay, but now I'm interested in my total cost for the whole 2 years. What numbers do I need to add up to find the total cost? Is the last column. That's what I want to add up, right? 3870 plus 4240 plus 4610 plus ... and there's almost 2 years of stuff in the ... and then the last number is this 41,980. So if we had Excel, this would be a good time, right? Because we definitely don't want to write all these numbers out, and then we don't want to type. Even if you had all the numbers, you still wouldn't want to type them on your calculator. So there must be a better way. But I'm just pointing out that adding up these numbers because of the ... is something that we really don't want to do. So here's the trick. We are going to take, so let's go to the 11 here, IDA, 11. Okay, so let's take a look. This sequence right here is an arithmetic sequence because we keep adding the same amount every time. Might not have been clear, but can you guys subtract these two numbers? Subtract these two numbers right here. Yeah, subtract. I want to know what the difference is. What's the difference there? Almost. 370? Yes? Now find the difference between these next two numbers. It's also 370, and the difference is always 370. So this is just another linear sequence. It's called an arithmetic sequence because we keep adding the same amount. So here's the formula if you happen to be adding the same amount over and over again. It says you take the first term and the last term, and you add them up. So here's our formula. Sum is equal to, I'm just going to write it in English. First plus the last. It says you add them up. You multiply the result by the number of terms. So multiply by the number of terms, and then divide by 2. I'm going to put the division by 2 right here. There's your formula. So in this example, first term is plus the last term. I'm going to divide that guy by 2. It's in a slightly different order than in the box, but it's the same. And multiply by the number of terms. Very careful here. Is it 103? Is it 104? How many terms are in that list? There's 104 terms in there because we started at 0. So that's what we have to find. This thing right here. $2,384,200. This thing better do my dishes for all that. I mean, seriously. I hope this is a fancy widget. Yeah. Okay, so that's the sum. Equals 384, 200. So I just want you to appreciate that formula that we used saved us from adding up 104 numbers, right? It's just kind of magical that it works. If you want to really know why it works, talk to me after class and I'll explain to you why it works. But it saved us from having to do a lot of grunt work, right? A lot of calculations. Questions on that? Okay. Let's go down to 12. Sana. Okay, thank you. So this problem quite similar to the one we just did. See if you guys can work with your table. You don't need to use the fancy formula, but I'm going to encourage you to use the fancy formula just to practice with it. So give it a shot, but take your time. Don't just go to the formula. Okay, so I've filled in my chart. First real common mistake to avoid is putting what number last? 5. 5 is the number in the problem, but the end of your 5th year is what we call 4, right? Because we started at 0. Now it's easy enough in this case to just fill in the PN column because it's 35 and it goes up by 5s. But if there were 100 numbers in the list, we wouldn't want to. And so I want to show you guys just to make sure that you can find this number, which to be honest, the first and the last are the only ones you need. But you can find that number using our formula. Our formula for this one was 35 plus 5n. That's the formula we came up with for this guy before. The 1,000 is a separate column, so it doesn't need to be in the formula. So for example, P4 in this case, because we're in year 4, is 35 plus 5 times 4, which is 35 plus 20, which is 55. So if you don't want to fill them all in, especially if there's 100 numbers, you use that formula just to zip you to the last number. That's all you need. Highlight here that 4 is that 4, and it gets thrown in there. Now adding 35,000 and 40 and 45 and 50 and 55 is not that big a deal. It's only 5 numbers. But if there were 100 numbers, I want you to be able to use the formula. So let's use the formula. Sum equals, what do we start with? 35,000 plus 55,000. That's the first one plus the last one. I take that thing and divide by 2 every time. And then I multiply by, why is it 5? 5 terms, however many terms. It can be deceptive. You can look at that and say, oh, there's 4 terms, but there's not, there's 5. And so if you very carefully do this calculation, what do you get? Thank you. Is that okay? Questions on the fancy formula? Okay, before the group activity, which is down below, let me tell you a real quick story. There was a second grade class. This is back a couple hundred years ago. Second grade class, the teacher kind of had a late night. Maybe he was out carousing around. Alcohol perhaps was involved. And he had a headache, and he didn't really want to be bothered with all these snotty little kids in his second grade class. So he says, okay, I'm just going to give these kids some busy work, keep them out of my hair so I can like go get some aspirin for my aching head, right? And so he says, okay, kids, I want you guys to add the numbers from 1 to 100. 1 plus 2 plus 3, all the way down to 100. And don't bother me until you're done. Now, this is a few hundred years ago, so the kids don't have these fancy calculators. In fact, they don't have calculators of any kind. So this is all pencil and paper. But in fact, it's actually not even paper. They had paper, but it was kind of expensive. So each kid has a little piece of like chalkboard, like a little slate, and a piece of chalk. And so what makes it harder to do this problem on like a piece of chalkboard, a small piece of chalkboard, than paper? is you're going to have to erase. You don't have enough room to do everything. Like you guys maybe take for granted the fancy notebooks that you have, but this is a luxury that wasn't always available to students. So they'd have to like do their intermediate calculation, erase some stuff, hope they don't erase something they need, and then do some more. Okay, so the teacher thinks that he's going to get like some peace and quiet, like half an hour at least or something, right? And the kids aren't going to get it right anyway at the end, but it doesn't matter to him. He just wanted some time. But a couple of seconds later, one of these kids writes down a number on his chalk slate and silently walks up to the teacher's desks, puts the slate face down on the teacher's desks and sits down. And the teacher is like, Carl, what are you, it's some kind of a joke. What are you doing? He flips the slate over and he sees the right answer. So I would like you guys to figure out the right answer to this problem. This is the right calculation. Are you sure that's the right number?
Should be. Right?
Lila says 5,050. Anybody else? Oh, a few other people say 5,050. So that's the right answer. So what did this little kid do? He did this fancy thing where you take the first and the last, you add them up, divide by 2, and then multiply by the number of terms, which was 100 in this case, right? Okay, so what's really impressive about this is he's a second grader, number one, and number two, the teacher hadn't just given them this formula the day before. The teacher had never shown them this formula. So this little second grade kid intuited that formula. He says, oh, here's a clever way to do it. I'm just going to add these things up and divide by 2 and then multiply by 100. So the kid, his name is Carl Friedrich Gauss, goes on to become like one of the top 3 mathematicians of all time. So this was a special second grade kid. Yeah. Yeah. No, you can look up the story. I'll give you his name. It's a history story.
You
No.
were just telling me that.
So Carl Friedrich Gauss, have we heard of him? So like top 3 mathematicians of all time. So he was something special. But let me tell you that he didn't do this by thinking of some formula. Like he didn't just like create a formula. Here's what he did. He says, okay, adding 1 plus 2 plus 3 all the way up to 100, that is very laborious to just do it straightforward. But the genius of Carl was to say, okay, I'm going to write this list backwards. 100 plus 99 plus 98 plus all the way down to 1. And he says, all right, here's what's nice. We're going to add them this way, column-wise. What do you get for 1 plus 100? 101. Okay, that's fine. Plus 101. Plus 101. Plus all the way down to 101. And adding a bunch of 101s is easy. What operation is it called when you add the same number over and over again? That's multiplication. How many 101s do we have? 100. So Carl said, okay, I've got 100 101s. So we do 100 times 101. What is that? That's 101 with 2 zeros, right? 10,100. How come that's not the answer? You're saying divide because it's in the formula. What did Carl made up a second list of the same numbers, right? He added the list twice. So this number 10,100 should be double the right answer. So I said, okay, we just got to fix this by doubling or by having it, and that gives us the 5,050. So yes, he was a second grader, and yes, he did this kind of calculation in his head, just the idea to reverse the list and do it all in his head and say, oh, it's just 100 times 101 divided by 2, and he did it in a matter of seconds, and he was really something special. Okay, so there's your history lesson for today. So take a look at the group activity. It's on the next page, and raise a flag if I can help.